coming to my talk. So my name is Jae Hoon. I'm a faculty at UCLA, and today I'll talk about finding effects on rare variants using extended pedigrees. And so this talk involves both method development and how we can use this method to real original sequencing data for bipolar disorder. So genome-wide associated studies, or GWAS, have found many common genetic variants associated with many different traits, as shown in this figure. But we also learned that those variants explain a small fraction of disease heritability or trait heritability. And there can be other potential contributors to the heritability, such as rare variants and structural variants. And recently, rare variants attracted great attention because it has been shown that those rare variants do indeed affect complex diseases and traits, and the next-level sequencing allows us to detect those rare variants. However, it is statistically very difficult to detect the effect of single rare variant because it's so rare. So a lot of different methods called collapsing approach has been developed. So this approach is trying to find the group of rare variants that influence the disease in let's say in a gene. And many methods have been developed, and some of them are shown here. And I also developed a few methods, and these are mainly for case control studies. However, even with these collapsing approaches, we will need at least thousands or more individuals to detect effect of rare variants, as Shamir and his colleagues show in this paper. There are a few large-scale genome sequencing studies nowadays that have sequenced large number of individuals, but still sequencing is very expensive. So is there anything we can do? And yes, there's also family-based studies. So one advantage of family-based study over case-control study is that the causal rare alleles may be enriched in certain large families, which increases its frequency, which means increased power. So this is a figure from paper by Zhu and Xiong, who show that families have higher power to detect effect of rare variants. So in this figure, the red line is the power of the three-generation family, and blue dots are the power of unrelated individuals. So families have clearly higher power. And family-based studies have several other advantages. So one of them is that we can detect and even correct the erroneous sequencing course made by next-generation sequencing by considering the Mendelian inheritance patterns of those rare variants. Yeah, and then there are many tools, several tools that actually correct the rare variant course based on the family structure and also sequencing quality. And with the family-based studies, we can also discover and study the effect of de novo mutations, and there are many de novo mutation studies. And family-based studies may be more robust to population structure, which may cause spurious associations in case control studies. And lastly, many families that linkage study collected before are still maybe available for sequencing, so the sample collection may be easier in case control studies. And those families may have large collection of phenotypes, which is another advantage. So in this talk, I will discuss two projects related to rare variant analysis for families. So the first one is to develop rare variant tests for extended pedigrees, and the next one is identify effects of common rare variants for extended pedigree for bipolar disorder. So to find the rare variants that influence the disease from families, there are many methods for rare variant analysis as well. So some of them are shown here, but these can only handle trios or small families, and these methods, mostly like scat-based method, can handle only quantitative traits, and they don't even provide software. So there are very few methods that can handle large pedigrees, both binary and quantitative traits, and affecting only pedigrees. And I will show you later. And these not every method can handle missing founders correctly. So this motivated me to develop a method called RarelBD. So the main idea of this approach is that the causal rare alleles are enriched among affected individuals while they are depleted among unaffected individuals. So I will first discuss high-level description of my method. So first, I assume that only one founder in a family carries a rare variant for each rare, carries the rare allele for each rare variant. So this is true for most rare variants because it is very unlikely that two founders carry the same rare allele, unless the family is very large, which I'll discuss next. And then any non-founders who have this mutation share this allele IBD. So we are interested in segregation of this allele, so this simplifies our IBD estimation. We then compute the statistic that measures enrichment of this allele in affected individual and depletion in unaffected individual. After that, we then take the burden approach that aggregates the statistics across multiple rare variants and multiple families in a specific gene. And we are trying to find if these rare variants influence the disease. Here's some examples showing what my method is trying to do. So in this family, there are 6 affected individuals and 6 unaffected individuals, and 3 affected individuals have mutation, and 3 unaffected have mutation. And looking at this variant is unlikely to be causal variant. So if you look at this family, 5 affected individuals have mutation, while only 1 unaffected have mutation, and this may be a causal variant. So my method is trying to find statistically whether the rare variant is correlated with the disease status in a family. So here's some math. So this is more specific information on my method. So we first look for variant where only one founder has a mutation. Then for such variant I in family J, our statistic Sij is basically the sum of number of affected with a mutation and number unaffected without mutation. We are then interested in the value of this Sij under the null distribution. So what we do is that we enumerate all inheritance vectors or IVs, and then estimate the mean and standard deviation of these statistics under the null distribution, assuming that certain founder K has a rare variance. So this is mean mu K and sigma K. And given this mu and sigma, we can compute G scores as this. And then we then take the weighted sum of these G scores across multiple rare variants and multiple families in a gene G. From this G score, we want to find the p-value from the standard normal distribution or genotyping approach, which I'll discuss next. So here I use 1S rotation because I assume we know which founder K has the rare variant. However, in your data, we don't usually know which founder has a mutation because their DNA may not be available or we just didn't sequence them. So this caused 2 problems in our approach. So the first problem is that we may not know whether only one founder has a mutation. And to solve this problem, we filter the variants according to minor frequency in the reference population, such as of the genome, or using the sequence families. So we want to only keep very rare variants. The second problem is that we need to know which founder has a mutation to compute the G score that I showed in the previous slide. But if we don't know the founder, then we cannot compute G score. So what we do is that instead of using only one founder, we use all founders. So we basically estimate the mu and sigma for every founder in each family. We compute the G score for each founder, and then we just average the scores. So this approach is called ORF approach. Now, another challenge in my method is that enumerating all IVs takes a lot of time. So if there are n non-founders, then there are 2 to the 2 times n possible inheritance vectors for IVs. So instead of using all IVs, we just perform random IV sampling, such as 100,000 IV sampling, to estimate the mean and standard deviation. And we found that mean and standard deviation do not change much after this number of sampling. So once we calculate the G score, we need to estimate p-value. And we found that approximating p-value from the standard normal distribution is not very accurate. So to show this, I just computed the first positive way of our method using 3 different pedigree structure we showed later at alpha 2.05, but the results show that the FPR is all lower than expected. This suggests that the normal approximation tends to yield conservative p-values, which means loss of power. And I don't show it here, but we also estimate weight from the data. And in such a case, the weighted sum of G-score is no longer estimatically normal. So instead of using normal approximation, we use what's called gene dropping approach to estimate p-value. So I won't show these details of gene dropping approach because time, but this is similar to permutation test. Basically, you generate the haplotypes of founders, and then randomly drop them to non-founders and calculate the statistic. And you repeat this many times to compute the p-value. So to test our method, we first generate simulations to measure the false positive rate and power of our method. So here's how we do simulations. So to generate the families, we first need to generate the haplotypes of founders. So we create haplotypes only related individuals using what's called POSI software. And then we then assign the rare mutation, one rare mutation to one founder in each family. And we then generate the haplotypes of non-founders. And we use 3D pedigree structure for this, which I will show next and later. And then given the haplotypes, we need to assign the disease status to each individual, whether they are affected or unaffected. And I will discuss in the next slide. We can then measure the false positive rate and power of our approach and advanced method. So here is how I determine whether individual is affected or unaffected in the simulation. So let PA equal to 1 with the probability that individual A is affected. So in the false positive rate, this probability is simply 50% because there's no association between genotype and phenotype. And in the power simulation, this probability depends on the logistic regression model that has several parameters such as baseline equivalence, odds ratio, and then also the genotype vector. And we also use several values of CI, where CI is the probability that the real variable I is causal. And in some of our simulations, we assume the top two generations are completely missing to simulate the missing founder case. So I mentioned that we use 3D pedigree structure in our simulations, and they are listed in this table. So we have like wide family, and big family, and small family. So we wanted to test how our method works not only for large families, but also for small families. So this is the result of false positive rate at alpha equal to 0.05. And in addition to my method, I tested two other software, FPCA and Pedgene. So they can handle both large families and also binary traits. There are 5 methods for FPCA and 2 methods for Pedgene. So the results show that our method has correct FPR, they are all around 0.05. For all 3 families, and both when all founders are genotype and when the top 2 generations are missing. However, for some methods, they don't have correct FPR, such as FPCA and high mean and t-square. So they are not included in the power simulation. And interestingly, the burden approach here, it has correct FPR when all founders are genotype, but it has inflated false positive rate when the top 2 generations missing. So this shows that this method doesn't correctly handle missing founders. So this is the power of my method and other methods. So here x-axis is the value of CI, where the CI is the probability that the variant is causal. So we change the CI from 10% to 50%. And the y-axis is the power. And the left figures are when power when all founders are genotype. And the
You
right
are in the Zoom meeting now.
Are missing. So the results show that our method is more powerful than all other approaches in all 3 families and all the CI values. And it is important to note that some methods lose some large power when the top 2 generations are missing, but our method doesn't lose much power except for the small families. We then apply our because I'm only the speaking. So. Okay, so we then apply this method to 2 real family data sets. So the first data set is early onset COPD data set. It has 347 individuals. This is high coverage whole exome sequencing data. and we have about 12,000 genes with allelic rare variants. One of the data set is Cleveland family study for sleep apnea in African American and European Americans. Their sample size around 500 to 600. This is SNP chip, the exome chip data, and we analyzed the European and African American separately. So this is the result of the method on EOCOPD data set. And the QQ plot shows that the influential factor, the lambda GC, is little deflated, but the p-value distribution looks normal. But we didn't find any gene with a significant p-value after multiple testing correction. And this is the result of other approaches. So, and the QQ plot do not look very nice. So basically, this Genotyping and Pedgene kernel, they have very high lambda GC, while CNC method is highly deflated. So it shows that this method do not generate uniformly discrete p-values. And this is the result of my method on the CFS European dataset. So the p-values are uniformly distributed with the lambda GC equals to 1.04. But again, there's no gene with a significant p-value. And these are the results for the other methods, and their distribution are not very uniform. So in Pedgene, both Pedgene approaches have a high lambda GC, and CMC and Genotyping have low lambda GC. Lastly, I want to show that our method is robust population structure. So there are two types of population structure for family-based studies. So one of them is within family, and the other is between family. So for the within family population structure, some founders may be from different populations. So it is a mixture of different populations in the same family. And some founders have many more or fewer rare variants than other founders. And I didn't show this, but this violates our assumption in genotyping approach that rare variants are independent. So to solve this problem, we remove the variants that are impact LD with another variant. And to test this, we generate simulations where only one founder has 4 times more rare variants than other founders. And then the results show that we have correct FPI for families. And another population structure is between family population structure, like our CFS dataset, where there are African American and European Americans. And because our method does the meta-analysis across families, our method is robust between family population structure. To show this, we merge the CFS-EA and CFS-EA, and we analyze them together. And then the QQ plot shows that the p-values are uniformly distributed. So in summary, we developed the rare variant association method for large families. We use the insight that for rare variants, only one founder carries a mutation, and we simplified IVD estimation. And we showed that our approach is more powerful than other approaches in simulations, and this method generates uniformly this p-value in the real family data set. And our software is available here. So next, I'm going to discuss our work of finding the effect of common and rare variants for extended pedigree for bipolar disorder. So the bipolar disorder, BP, consists of episodes of mania and depression. And it is common complex disorder, and it affects millions of individuals. And there are a few different types of bipolar disorder, such as BP1, BP2, cyclosemic disorder, and other bipolar disorder. And BP1 is considered to be the most severe form of BP. And it has quite high heritability, estimated 80% from twin studies. And there are a few large-scale BP GWAS, mainly conducted by Psychiatric Genomics Consortium. The first one analyzed about 4,400 cases and 6,200 controls in 2008. The second one analyzed about 12,000 cases and 51,000 controls in 2012. The latest GWAS, which analyzed about 30,000 cases and 170,000 controls, found 30 loci associated BP, and it was just released in Nature Genetics. And like BP, schizophrenia is another major psychiatric disorder which has high heritability and comparable to that of BP. And interestingly, schizophrenia GWAS found many more loci than BP GWAS. So in this schizophrenia GWAS analyzed similar number of cases and controls as the latest BP GWAS, but it found 108 loci associated with the schizophrenia, but the latest BP GWAS only found 30 loci. So what may be causing this difference? So one possibility is that there's a greater heterogeneity in individuals with bipolar disorder because there are different types of BP, such as BP1 and BP2. And another possibility is that the higher proportion of BP may derive from the variants not in SNP chips that GWAS analyzed. So basically rare variants. So there are actually several studies that have already tried to identify rare variants that associate with BP using families, and some of them are shown here. For example, Amento et al. Show the effect of rare variants in neuronal excitability gene on BP using the BP family. And there are a few other studies such as whole genome sequencing in genetic isolate, a couple of family-based studies, exome sequencing studies, and this study looked at the specific genes and the rare variant, segregation rare variant in this gene. So to study the impact of both common and rare variants on BP, we analyzed 26 extended pedigrees affected by BP1. So our pedigrees are from 2 Latin American populations. So 15 pedigrees from the Central Valley of Costa Rica and 11 pedigrees of Antioquia, Colombia. So our study focused on exclusively on families ascertained for multiple cases of BP1. So it means that each family has at least 2 individuals with BP1. And we believe that this would reduce heterogeneity between BP1 and other milder forms of BP, such as BP2. And we focus on families from 2 Latin American populations that are considered closely related genetic isolates, which will further reduce heterogeneity. As you can see, our pedigree size vary from 12 to 355 individuals, so some families are really large, and there are 2 to 44 BP1 individuals per pedigree. So here is how we genotype and sequence our individuals. We have total 1,439 individuals from 26 extended pedigrees, and we genotype 856 of them using only 2.5 million microarray. And among them, we sequence 454 individuals using exome-pick software to choose which individual to sequence. And these were selected for sequencing because they would provide good amount of information to impute the genetic variants in the remaining family members who were not sequenced. So we performed the high-coverage whole genome sequencing at Illumina, who performed the variant calling using their own variant caller called Cassava, and they also sent us a BAM file. And actually, in CGSI, we discussed a lot of tools. So this is actually usage of these tools. So we first called out several different types of genetic variants. So we use GATK to call SNV. We use the genome tree and CNV to call CNVs. We use Lobster to call SDRs, and we use de novo to call de novo mutations. And we then perform very stringent QC to obtain high-quality genotypes for each type of genetic variant. And we also perform the genotype refinement using polymer software. So as I mentioned before, this software corrects the genotype based on the sequencing quality and the pedigree structure. We then perform the genotype imputation that considers the family structure called GG software. So this software imputes individuals who are not sequenced in a family, and it has high accuracy in imputing rare variants. So using this whole genome sequencing and using this whole genome sequencing microarray data, we try to evaluate the impact of both common and rare variants on BP1. Specifically, we focus on 2 major questions about the genetic etiology of BP1. The first question is the overall genetic architecture of BP1 in these pedigrees. So we are trying to ask, what's the overall contribution of genetic variation to this disease? And we use a burden analysis to answer this question. So for the common variant, we calculate the polygenic scores and compare the PRS between BP1 individuals and their related controls. And for rare variants, we compare the burden of rare deleterious variants in a specific gene set that we consider to be related to BP1, which I'll discuss next. And another question we focus on was finding the genetic loci segregated with BP1, and we call this segregation analysis. And for common variants, we use the linkage analysis. And for rare variants, so we develop actually new method after RarelBD for this method, which I'll discuss next. So here's how we process the data. So we use a bunch of different software to code the variant, and we apply polymer to only whole genome sequencing SNV, and included only the SNV and CNVs. And as you can see, there are different number of BP1 individuals with controls for different types of genetic variants because the QCs are different. And these are the analysis that we use each genetic variant for. So I'm skipping a lot of details about our QC and imputation because of time. So I will just directly go to the polygenic risk score analysis to find the version of the common variant and see when we did this one. So to calculate the PRS, we use the two GWAS summary statistics. The first is the PGC GWAS statistic for BP1, and the other is the Schizophrenia GWAS statistics. And using these summary statistics, we calculate the PRS of our samples that consist of 190 BP1 individuals and 130 controls using whole genome sequencing data. So we use the PRSI software, and we calculate the PRS separately for BP1 and schizophrenia. And so the PRS is calculated, a PRS for ICE individual is calculated as really sum of the risk allele that this ICE individual carries across a certain number of SNVs. Okay? Where the effect size, the beta J, is from the summary statistics. It's like the odds ratio. So the higher PRS means that this individual has higher polygenic risk for the BP1 or schizophrenia. And we want to test the association between PRS and then the BP1 status. And we use the two regression model. One is the linear mixed model that models PRS as a dependent variable and PG status as predictor. And the other model is generalized linear mixed model, which is the other way around. And both approaches took into account the family relationship and global estimate of admixture, which I'm not showing in this talk. So this is the result of PRS using BP1 summary statistics from PGC. So we observed association p-value less than 0.05 for 2 GWAS threshold for LMM here, and then 1.01 threshold for GLMM. So in all cases, our BP1 individuals had higher mean PRS than the related controls, as shown in this box plot. And we didn't observe low association p-values here for the more significant GWAS p-value threshold. And we think that this is because there may not be enough SNVs to calculate the PRS. So this shows that our BP1 individuals carry higher polygenic risk for BP1. We are then interested in how much higher polygenic risk our BP1 individuals carry compared to controls. So we look at the variance explained by PRS. So these are the R-square values for different GWAS threshold, and we observe the largest R-square, which is 1.5% at 0.01 threshold. And it is important to note that this is noticeably smaller than the variance explained by PRS in the latest PGSP GWAS, where they observed the weighted R-square is 8%, while ours is 1.5%, it's not 50, it's 1.5%. So one explanation for this is that the population difference between the PGC and our pedigrees, because PGC are mostly Europeans, while our pedigrees, they have substantial component of Native American and African American. But we found that more than 90% of SNVs in PGC are present in our pedigree. So but we didn't look at the allele frequency difference. But many of the SNVs are in our data set. So we consider it unlikely that this population difference solely explains the difference in R-square between PGC and our samples. This also could be due to because our controls are closely related to BP1 individuals, so they may carry some polygenic burden for BP1. Or simply our BP1 in our pedigrees are less polygenic than BP1 in population samples. This is the result of PRS using the schizophrenia summary statistics. And previous PGSP GWAS found that PRS estimate from the schizophrenia GWAS explains the variance of the BP. But in our pedigrees, the PRS estimate from the schizophrenia GWAS is not associated with any increased risk of BP1 at any GWAS threshold. So this may reflect another different characteristics between characteristic of BP1 between BPGC and pedigrees, and because our pedigrees were ascertained for multiple closely related cases of BP1. Next, we are trying to look at the burden of rare deleterious variants in our gene set. So basically, I'm going to discuss this gene set first, and this was worked on by Su and Alden. So we just cannot compare all the rare variants between case and control. So we focus on some specific genes that are more likely to be related to BP1. So to find those genes, we first ran the stratified LD score regression using the latest PGSP summary statistics. And we tested 10 cell type groups here that the LD score regression paper tested. And we observed the significant enrichment of BP1 heritability only in the central nervous system cell type, which is consistent with what they're finding. So we use this region, which contains 8,714 genes. And second source we used was 99 genes near our peaks. And we also used the latest PGSP-BP1 GWAS result. We found the 72 genes near the BP1 GWAS hit. So after merging these resources, we have 8,757 unique genes that contain at least one deleterious SNV. So what's deleterious? So I'm showing here. So here is how we define rare and deleterious. So basically, because of time, I'm going to skipping this, but basically we use both external source, like Water and Genome, XJ for SNV, and database genomic variant for CNV, and Water and Genome for CNV, for whole genome sequence CNV, to find the rare variants. And for the deleterious variants, they are stop gain, stop loss, splice site, and damaging variants of polyphen 2. So you can see that we only focus on coding variants. So using this criteria, we have 25,000 rare deleterious SNV in our gene set. And for CNVs, we have about 2,200 rare array CNVs and 4,400 whole genome CNVs. So we take more CNVs with the whole genome sequencing data. And using this rare variant, we calculate the burden score. So the burden score for SNV is the mean burden of rare deleterious SNVs in the gene set. So this is the number of rare deleterious SNV that each individual carries. And for CNV, because the gene can overlap multiple genes, this is actually the number of genes in the gene set intersected by rare CNVs. We then have to adjust these burden scores for the all rare SNV for SNV and the total number of CNV for CNV. So this is necessary because individual may carry more rare deleterious variants if she or he carries more rare variants overall. So we are correcting for that phenomenon. And after this correction, we quantity normalize the residuals and then test the association between these residuals and BP1 status using the same LMN and JLM approach. So this is the result of burden of rare deleterious SNVs in the specific gene set that we found. So the results show that our BP1 individuals have higher mean burden of these rare deleterious SNV in the specific gene set. And the p-value is barely less than 0.05. And this is the result of burden of rare CNVs. So you may have to see, but there are 5 different CNV types. The top one is the all array CNVs. The next one is the duplication from array CNV. The next one is the deletion from array CNV. The next one is the all whole genome sequencing deletions. The last one is the whole genome sequencing deletion covered by enlisting SNVs in the microarray. So we are more confident on these CNVs. The left one is the result of GLLM. The right one is the result of LMM. So the results show that these are the odds ratio and this is 1. So odds ratio greater than 1 means that our BP1 affected individuals, they have more genes affected by rare CNVs, and they are significant. The previous CNV studies, they found no global enrichment of rare CNVs in BP1 individuals, but they focused on CNVs greater than 100 kb, which is kind of large. But so they just look at the overall CNVs across the whole genome, not just specific genes. So similarly, when we look at this genome-wide average number of CNVs across the whole genome, we didn't find a significant difference between BP1 individual and controls. So this result suggests that the impact of CNVs may be restricted to specific genes, like our gene set, or may derive from the smaller event that the previous study didn't test. So I'm skipping the linkage analysis because of time, and I'm going to go to the segregation of rare deleterious variants in a gene set. Yeah. So we are interested in finding rare variants that are present in affected individuals while they are not in unaffected individual, and this is what we call segregation. And as I show in the first part of the talk, I developed a method called RarelBD, which is scalable, but it assumes that only one founder has the rare variant. And this assumption may be violated in some of our large families because some families have more than 300 individuals. So it is possible that multiple founders carry the same rare variant, depending on how you define rare variants. So in this approach, we came up with a different approach to find the segregation. So basically, instead of assuming only one founder having a rare variant, we allow multiple founders with a rare variant. So we call these founders FRB, so they are the founders who introduced the rare variant to the family. And we, for now, let's assume that we know these founders. Then our statistic is same as before, is sum of number affected with rare variant and number unaffected with rare variant. And given this S-rare statistic and FRB, we enumerate many random ID sampling, assuming that those rare variants come from this FRB. And then we can calculate the distribution of S-rare statistic. Then we can then compute the p-value of this statistic by finding the proportion of IDs that generate the same or more, larger S-rare statistic. So our approach is different from RarelBD because it allows multiple founders with rare variants. So let me just give you the example. So in this family, we assume that all individuals are genotyped, and individuals 9 and 10 at the bottom, they are affected, but the rest of them have missing phenotype. And we perform 10,000 random ID sampling to estimate the p-value of each S-rare statistic. So when one founder one at the top has a rare variant, the p-value of S-rare value 2 is about 0.0. However, when found 8 has rare variant, the p-value for same S-rare statistics much larger, is 0.25. So 2 means that both affected have the mutation, rejected the mutation. So the fact that the rare variant is inherited in every generation and shared by the affected individual in the last generation, it is a more rare event than when the rare variant is directly inherited from the parent. So that's why this one has more significant p-value. And again, I'm skipping a lot of details because of time. Including how to find the founders, but I can discuss offline. So this is the result of segregation of rare SNVs. So we tested about 6,400 rare SNVs in our gene set. So we calculate the p-value for different levels, like gene level, variant level, family level, but none of the p-values are significant after multiple testing correction. So we look at the top gene more carefully, which is ASTR1B gene. So it has one damaging rare variant on chromosome 2 from CR2 family. So this is our largest family. And this one does not appear in 1,000 Colombian population, and it is very rare in exact AMR population with a 0.04% of minor frequency. However, this is quite relatively common in our data set, with minor frequencies about 2% in all families and more than 6% in this family. But this doesn't account for relatives. And interestingly, the previous CNV analysis using WTCCC data, they found a large duplication around this gene associated with schizophrenia, but it didn't replicate. So the S-rare statistic for this gene is 46. There are 7 affected individuals with rare variants and 39 unaffected without the rare variant. But this is not the perfect segregation because there's a higher S-rare values, like here, 47, 48, possible. This is the segregation of rare CNVs. So we tested 314 rare CNVs in 251 genes, and again, no genes are significant. So we look at the top gene again. So it has one rare, relatively small deletion in one family, and it is quite common in this family, like 14%. And previous linkage study for schizophrenia found a linkage peak around this gene, but it was not significant. And interestingly, Thomas et al. Recently found a duplication in this gene, segregating with BP on the family-specific linkage peak. And again, it was not perfect segregation because there is a higher SNV value. So in conclusion, we first tried to identify the genetic architecture of BP1 in these pedigrees. So we found that the BP1 individuals have higher PRS, and they carry higher burden of rare deleterious SNV as well as rare CNVs in the specific gene set that we came up with. And I didn't show here, but our linkage analysis found 50 pigs, and we developed new method to find the rare variant segregation, but we didn't find any rare variant with a very strong effect. So these results suggest polygenic genetic architecture of BP1 in these pedigrees, where there are many common and rare variants with small and moderate effect sizes, rather than like few large effect rare variants. And it is also possible that there may be non-coding variants that play an important role in BP1 in this pedigree because we didn't identify any BP1 associated coding variants. And I'd like to thank everybody involved in these two projects. I'd like to thank all my lab members, and thanks Sue and Alden who work on the various parts of the BP analysis, and I thank Nelson who directed this study. And I'd like to thank the PGC and Costa Rica and Colombia groups who share the data with us, and I'd like to thank everyone.